Hi guys, welcome to the Advanced Refrigeration Training Podcast. I'm your host, Kevin Compass, along with my partner, Brett Wetzel. Today's episode is sponsored by Westermeyer Industries, the leaders in oil management and pressure vessels for the commercial refrigeration industry. Whether you're involved with designing a system or tasked with servicing one, Westermeyer Industries has been helping meet the needs of customers like you for the past 20 years. They offer a broad catalog of stock system components with an in-house team of engineers to assist with custom solutions as well. From oil separators and heat exchangers to system monitoring devices, Westermeyer Industries are a total system specialist with industry expertise, engineering know-how, and the manufacturing muscle to help you tackle problems and deliver solutions.
Go.
Hi, welcome to the Advanced Refrigeration Training Podcast. I'm your host, Kevin Compass, along with my co-host, Brett Wetzel. And tonight we're going to talk about Copeland IDCM controllers for controlling digital compressors. So, Brett, you want to take the lead?
So the reason why we have IDCM controllers for these particular compressors is for steadier suction control. One of the worst things for any system is the load to fluctuate. This causes an imbalance in the load, causes the BTUs to basically change, throughout running, and you get, these spikes of high pressures. And this way, with having this type of digital unloading, controls the suction pressure a heck of a lot better. So you get more of a straight line. I know Kevin has posted a bunch of tuning that he's done on a bunch of racks, showing before and after pictures of after setting up a rack with an IDCM versus what it was before. Basically, a lot of a regular standard unloader basically just, if you have let's just say, for instance, you have a 4D. If you have a 4D, then basically that 4D might be 20 horsepower, and then when you unload half the heads, basically now it's a 2D. So basically you can unload it off and on like that. With the IDCM, you don't have to go from 100 to 50, 100 to 50. You could actually load that compressor from 50 all the way up to 100 in increments using the cycling on that solenoid. Same thing we can do with scroll compressors as well. That's done a little bit differently. The way it is done with scrolls is basically the male and female rotors of a scroll. If anyone's ever taken one apart, are basically touching, and there is usually a copper line on the top of the head of the compressor, and that copper line is then connected to a solenoid, and basically that solenoid, what it's doing is actually relieving the pressure from the top of the head going into through the solenoid back into the suction. And basically what that's doing is actually separating the rotors. As you're separating the rotors, you're actually reducing the amount of compression that it's doing. And once again, you can unload that compressor from downwards of 10% all the way up to 100%. So you have more of loading and unloading capability without having to add cycles onto your external compressors. Making sure your loads are good, making sure your suction pressure is extremely important when doing this. But that's just to give you a brief overview of what these things are actually doing and why we have them.
That's a good overview. So what we're going to go over tonight is off of the Emerson Bulletin. It's AE Bulletin 1328, which is the IDCM controller bulletin. So everything we're going to be going over is going to be inside that bulletin. So for you guys' reference. So this IDCM controller is basically a pulse width modulation controller that gets a signal from an EMS controller in the form of a 1 to 5 volt signal if it's a 3D or a scroll. And if it's a 4D and 60, it's going to be a 3 to 5 volt signal, DC signal. So the way this is set up, so you're going to have all these terminals on this board. You have a 24 volts terminal. I'm going to stress this, that polarity is of the utmost importance with the 24 volts and with the actual signal wires, because if you take this board apart, the commons on the signal wire and the commons of the 24 volts inlet are all the same common. If you flip-flop those, you will blow up the EMS board. We're going to go over that a little bit later when we go into the troubleshooting part of this. But polarity with the signal wires in the 24 is of utmost importance. So this controller is controlling the compressor contactor, your unloader solenoid, like it's pulsing the solenoid. It's using pulse width modulation to pulse this solenoid on. So it's checking the DC voltage coming from your EMS board, and whatever it's at, according to the pre-programmed thing in the controller, it's going to pulse that solenoid on for so many seconds, off for so many. And then it's going to keep doing that until that DC voltage changes. Okay. And then you're also controlling your vapor injection off this if you have it. And then you're also controlling your alarm contact on here. Now, there is CTs built into this. Some, I know this was talked about online the other day, some manufacturers use all three lines. You should run all three phases through there. But if you only have one phase running through, it has to go through the C terminal, and it works fine. I mean, I don't know how many protocols. We got to have over 150 protocols that are wired that way, where Husband only took the one wire through the C. So that'll work fine. And then this controller has a bunch of alarm functions on here. So I think first we're going to go through these actual alarm functions, and then we're going to go over more of how it stages everything inside the controller. So if we go through these alarm functions, like the most common one I see, which Brett, I don't know about you, but is demand signal loss. So demand signal loss meaning if it's a scroll or a 3D means the DC voltage drop below the 1.44 volts for how many seconds, and it shut off the compressor. I'm sorry, it's below 1 volt, I believe. And it's 1.44 volts for it to come back on. So this could be a EMS issue. This could be the way that they have this set up in the controller. So the way the output is scaled. So if it's a 3D or a scroll, its minimum position is 10%. So if you have a 1 to 5 volt signal, you need to make your minimum 10% of that 1 to 5 volt signal, so that way you don't lose that. It doesn't ever go below 10% and drop out on the demand signal loss. So you want to make sure that you're above that 1.44 volts, or else it's going to lock out. So I'm sorry, I said that wrong. It's below 0.5 volts DC. It'll fault on demand signal loss.
Or you basically, if you have it anywhere like at 1 volt, that contactor will actually disengage.
Yeah, correct. And then it'll drop out and the alarm contact will close. So then you'll be getting these random IDCM alarms, and that'll be for it. I see this a lot. I see the scaling set wrong in the controllers, and this causes all kinds of nuisance alarms. So then you have a couple other on here, so there's a discharge thermistor on here, and if you are using demand cooling, there's a resistor in here to place in there to jump out this particular alarm, because you want the demand cooling to control the liquid injection and the actual alarming functions of it. So if you're getting a medium temp compressor or a low temp compressor that doesn't have demand cooling, it's going to have a discharge temp sensor on there to protect its compressor, especially the scrolls, because with the digital unloading on the scrolls, I mean, they could overheat if they're running at the minimum position for too long. So this discharge thermistor is on there to make sure that it's not going to overheat the compressor. So that's one thing to watch out for. Then the locked rotor alarm.
Kevin, hold on.
Yep, go ahead.
Hold on. Let me try something. I'll just edit it out. That's fine. I want to see if it's my internet connection or yours, because you keep flaking out where it sounds like you're underwater. So let me see if I can just turn on my hotspot, and I just want to try this. Bear with me 1 second. All right, can you hear me?
Yep.
All right. I think that might be better. Oh, awesome. Then apparently my internet sucks. One of the things I did want to add when you were talking about the demand, making sure that you're, typically you always want your time delays to be set to make sure that it doesn't short cycle the compressor upon an abrupt, turn off and turn back on. One of the things I can disagree with is with the IDCM module. A lot of times, you start off your compressors, from number 1, over, you start 30 seconds, a minute, minute 30, 2 minutes, and so on and so forth, as, however many compressors on your suction group. On anything with an IDCM, just put it to 0. Don't screw around, because what will happen is if the controller has its signal and the RO is calling for that particular compressor to be on, and it doesn't sense that amperage within a certain amount of time, it's just going to flake out and fault out, and then you're going to be required to pull the control power off of the IDCM module to get it back up and running.
Yep. Yeah, it's one thing to be really careful about this. Like, if I don't know why all these manufacturers don't put a switch to kill the 24 volts, or when I'm doing these installs, I always wire the power for the IDCM transformer. I try to keep it on a separate transformer. I always wire the power coming off that compressor switch. So if you shut the compressor switch off, then it kills power to the transformer so that it resets the board. Because having to pull a wire off of a controller to reset it is just stupid. But that's how 99% of these are set up.
Well, that switch is probably what, $2? You don't want to put that switch in there. You have to pay someone to drill the hole. It gets expensive.
Yeah, I mean, really stupid. I mean, so yeah, that's one thing. Like, one of my pet peeves. You be careful. I've seen many guys short off that transformer trying to pull that. A little strand of wire hits the common, and then poof, she's done. Okay, and then so. The high discharge temperature fault on these locks out at 260. I'm sorry, it locks out at. I can read that.
Wouldn't it be like 310? Just like the regular.
Yeah, it is.
Okay, because it would be comparable to the demand cooling module. Those shut off at 310. They engage the liquid line solenoid at 282 and kick them on at 292 and kick it back out at 282. You might think that that's a high temperature, but if you got to remember, that these the sensors are internal in the head. Okay, so I'm not talking about actual discharge line temperature. I'm actually talking about head temperature. And you got to remember, there's usually like a 75-degree difference between the two. So, you're basically kicking this thing on at 217 and 207. You're basically just riding the line there, just kicking it back and forth. And then finally, if it gets up to 227 or 237, and it'll end up tripping out and opening up that set of contacts in the IDCM, or same thing with the demand cooling module as well.
Yep. So the next real common code is going to be the code 3, which is compressor protector trip. So this goes off anytime that the IDCM does not see the compressor running and the supply voltage for the signal is above 1.44 volts DC, and it does not see the compressor running from one of those CTs. It will fault out on compressor protector trip. Now, this could be a safety issue. You could have an open safety. It could be off on oil. You could be overheated, but it doesn't see the compressor running when it's calling for it to run. So that's when it's going to lock out on compressor protector trip. So this is a very, very common one. I would say compressor protector trip and code 5 demand signal loss are going to be probably 90% of what the alarms you're going to see. So those two are going to be the most common ones you're going to see. And then, like I said, that could be a safety issue. If it senses that compressor protector trip, it's going to open up M1, 2, which is going to be your contactor control. So that way, you want to make sure that you're going to have to recycle that power again to troubleshoot it to get the M1 and M2 to close again. And then another real common one is the code 4, which is locked rotor. So this condition occurs when a compressor is sent, when the compressor CT is sensing 4 consecutive startups with high amperage in a 20-second period. So if in the 20-second period, if it sees the, CT sees the amperage skyrocket through the roof, it's going to think that it's throwing locked rotor. I mean, this is a common one. I mean, this could be caused from like rapid cycling. So if something's shutting everything on and off, I mean, I've seen them cause nuisance code 4 lock rotor alarms, or you could have a failed CT inside of the IDCM that's causing it. But yeah, that's generally what it is. You want to add anything to that, the alarm section, Brett?
Well, we were talking about before, especially if it's a low temp compressor, you could have the vapor injection solenoid, valve stemmed in, basically cause it to go backwards, which could potentially cause it to do lock rotor because it has that excessive, the excessive inrush. The one that you were talking about with the safeties being open, that's where you're going to see if the time delay is energized, and then there, it's either, I forget how long it's instantaneous. I think like if it doesn't actually pick it up as soon as it has the signal in the call, it potentially will alarm out where you basically would then have to drop the 24 volts from that. That's all I got for that.
Okay. This is for all electronics. One thing to really watch out for is the actual 24-volt supply. Make sure your transformer's tapped right. See this all the time. See transformers tapped that are tapped for 230 and they should be tapped for 208, and you're getting a low voltage. If the voltage drops below 18.5 volts, it locks the controller out on low voltage, and it's only a 1 volt increase for it to unlock. So I mean that can be causing nuisance alarms. So you want to make sure your transformers are tapped right with the actual rack itself. You want to make sure all your transformers are always tapped right.
And remember, so in the summertime, your voltage is gonna go down. Because basically there's more of a demand on the grid. You'll see this a lot in inner cities. Philadelphia, we used to have to put current protectors, phase loss monitors on a lot of our stuff because in the city, in the heat of summer when it was 100 degrees, it doesn't really seem like a lot, but in Philly it is. The grid, a 208, 230 circuit would go all the way down to 182. 190, somewhere in that wheelhouse. And if that happens, obviously you're going to have a higher higher amperage because you have a lower voltage. Keep that in mind, because that could be happening if you happen to see calls happen a lot during the day, and then by the time you get down, but let's just say alarm's out at noon. You guys are swamped. It's summertime. By the time you actually show up on site, you can't find any known reason why this thing would have tripped out, right? Because now you reset it, it's back up and running. You can't figure out why. Keep that in mind, and that you can keep that in mind as well with working with rooftop units. I've done plenty of calls where I showed up and the unit, was running hot, wasn't actually pulling down temperature. You show up, later that night because you guys are slammed and you guys are running a little bit behind on calls. Then everything's working fine. Then you check the voltage and you're like, well, it's 23.8. That shouldn't be a problem. But that's at 8 o'clock at night. That's not in the middle heat of the summer, in the middle of the day, where you could be potentially dropping that voltage all the way down to 18 or 20 volts, like Kevin was saying prior. So just be mindful of that. Your ambient temperature can and will affect your temperatures going to a lot of your electronics, and it can do some screw stuff with it. You were also stating before about making sure that you have the common and the hot on both of those, set up properly. Anything that uses an analog output module, you have to make sure that does happen. We had an instance where we had, I know we're talking about IDCM, but the Hoffman controllers that control the condenser fans on the Seasons 4s and those type of units, those generate their own voltage. And I had found where the schematic was actually wrong. We blew up a controller and then blew up another one. And I went out there and I blew up one, and I contacted the manufacturer. He's like, well, you have it wired wrong. I said, no, I have it wired per the spec. And, he's like, well, what model number do you have? And it was like one model number off than what the actual manual said. He's like, well, that's why it's this one. It's supposed to be switched opposite. I'm like, but the schematic's wrong. So he ended up sending me an abridged schematic, and I called him a week later, and he was fixing all the schematics and the rest of the boxes that they had to send out for all the controllers, because they couldn't figure out why they had a extreme amount of losses. But just keep in mind, heat affects your voltage, and making sure that polarity is correct.
Yeah, it's a good thing to check. So on these actual IDCM controllers, if you look at the actual wiring diagram for it, so L2 on the actual controller is what is doing all the switching. So that is your actual switching. Now, M1 and M2 are going to be your contactor coil voltage. Now, these are not relays in here. These are Triacs. Okay. A Triac is a solid state, very it's a solid state relay basically, but it cannot handle current whatsoever. So this is not made to handle current. If you have a short of any sort, whether it be a contactor coil, wire rub through, it'll blow it. It'll blow a Triac. I mean, it happens all the time. I see guys in there all the time. They can't get power out of M1 and M2, and they're getting a code 4, which is compressor protector trip. It's not seeing it run. They reset it, and then they get no power out of M1 and M2. So generally, when that happens, you shorted up a Triac. So you're not getting any voltage out of it because you have a shorted Triac. Now, don't just throw this new controller in there and not check the contactor coil. Take the wires off, ohm it out, make sure it's not shorted, or start tracing your wires out, because somewhere in that wiring is a short, and that IDCM is going to go before any fuse will, because that Triac is not rated to take that voltage, or that amperage. So
besides checking, obviously, the coil to make sure that you have good resistance, to make sure that's not shorted, Also check your safeties. Low pressure switch, high pressure switch. If you have a head temperature sensor, or head temperature, like a high temperature discharge line, check across. If you have no power on the system, and basically you go across it on ohms, you'll get 0.01, maybe 0.1, 0.2. If you're getting a half a ohm, if you're getting 1 ohm, there's a problem with that switch. By doing that, you're going to drop voltage across, that particular switch, which means that's going to drop voltage, which means you are going to drop voltage even more in your contactor and cause the amperage to be excessive. Because you got to remember, all the safeties are in series, right? Series aren't made to have loads going in. Well, basically, if you have a faulty low pressure switch, high pressure switch, oil safety, and it's, let's just say it's pulling 5 ohms. Now that actual switch has now became a load. So now that load is actually going to drop voltage across it, which means you're not going to get the proper voltage across your contactor coil, which means you're going to pull excessive amperage, which means, eventually you are going to heat up that coil, and it is going to go bad. So just be mindful of that. It's not just checking, the coil to see what happened, but also check the rest of your safeties. We've had a multitude of issues, especially, when people are changing out compressors. I always say just change out the safety that you're changing out with the compressor. And the reason why is, we don't know why that compressor went bad. You know what I mean? There could have been some other reason that we couldn't diagnose, unless you did a tear down and found out it's something mechanical. Then it's something that wasn't necessarily electrical. But that being said, that mangled compressor inside could have been caused by a faulty oil fill control. Well, it's a lot easier to put another $400 controller in there than have to change out that $10,000 compressor again and again and again. So I just want to preface that, a lot of times it's a lot wiser to just change out the safeties with, what you're doing. And those IDCM modules aren't cheap as well. Kevin, what do they run?
They're like around like $400 or $500, I'm pretty sure. So yeah, they're not cheap. So I want to go over. Go ahead.
Is there a difference between the IDCM for the scroll and the like the 4Ds?
The scroll and the 3D are the same IDCM part number. The 3D or the 4D and the 60 have their own IDCM part number, so they are different.
Okay.
The only difference that I know of is the actual output scaling in it. But I want to go over on how to test the compressor outputs, the M1, M2. So this is right in this manual, and it works pretty good. So what you do is you're going to want to power down the controller. You're going to want to take the wires off C1 and C2, which are going to be your input voltage from your controller. You're going to want to wire P3 to C2, and you're going to want to wire P1 to C1. Now, what that's going to do is that's going to put the full 5 volts on that controller. So that should cause M1 to close, and that should cause M1 and M2. It should be sending 120 volts or 208 volts, whatever your control voltage is, across them. And so should your unloader coil. So if you're not sending out voltage at that point, and when you power that thing back up, if it's not sending out voltage on M1 and M2 and the solenoid power, then with a full 5 volts at it, then you have a faulty controller. If it is sending out the proper voltage, then you have some other problem. It could be an EMS problem along those lines. But that's how you test the contacts on that controller. You'd be sending it a full 5 volts by jumping P1 to C1 and jumping C2 to P3. So that's going to send a full 5 volts to it. Now, like we said before, those Triacs do not handle the shorts very well. So the other thing to keep in mind, so there are several versions of these IDCM controllers, like Brett was saying. So there's one for there's a refrigeration scroll, which would be that'd be the one that's also the 3D. So the duty cycle time on that is 20 seconds. So that's 20 seconds on, 20 seconds off, 20 seconds on, 20 seconds off. Okay, the air conditioning scrolls is 15 seconds, so it has a less of a duty cycle time. And then you have the 4D one, which is going to be your 40 and 60. That is also a 20-second duty cycle time. So that is the pulse rate time on the solenoid. So each one of these controllers has its own part number. So you need to pay attention to that. If you're working on a 3D, you need to make sure it's the 3D and scroll one. And if it's a 4D or a 60, you need to make sure it's that one, because A, your voltages aren't going to match for your signals, and then B, it's just not going to work properly. So on startup, I've seen that a couple times where they've had the wrong ones. And so if you go down like on the tables where you start listening, like on page 7 of this manual, it'll tell you like your demand signal so at 3 volts is 50%. Okay, so it's gonna be loaded for 7.5 seconds and unloaded for 7.5 seconds. So it's 7.5 seconds on, 7.5 seconds off, and then same thing if it's 5 volts, it's always going to be loaded. It's not going to be unloaded. If it's at 1.44 volts, which would be 10% of 1 to 5 volts, it's going to be loaded for 1.5 seconds, unloaded for 13.5 seconds. So you can see it's pulsing that unloader on and off, and it's changing the times based on what that DC signal is. So that's how it's causing this pulse width modulation to load and unload.
So I had a question for you. You have more experience with these. I mean, I've troubleshooted a bunch, but just not set them up. I was looking at programming set up on E2, and there was basically like an amount it was looking at as far as its timing. What's that supposed to be set for? As far as I think it's like seconds before the controller makes a change and tells it how fast it wants it to react. This particular
Emerson one. Go ahead. Sorry.
Right.
Go ahead.
So the controller was set up for 10 seconds. Is that too slow? Should it be lower than that?
Generally, it's set to 20 seconds.
Really?
Yeah, it's usually a 10% minimum with a 20-second cycle.
Okay.
That's generally what I see them set at. That's generally what I put them at. So if it's a 4D, it's going to be a 50% minimum. Mm-hmm. And then if it's a 3D, it's going to be a 10% minimum. And same with the scroll, it'll be 10%. So I mean that is critical when you're setting these up, because they will not operate properly. And then on the back end of that, you have to make sure your scaling is right on your analog output, because with Emerson, when you make an analog output, it starts out as a 0 to 10 volt no matter what. That's the stock setting for it. So you have to change it to 1 to 5 volts. So that way it'll go from that. And then the actual E2 is going to rescale that, because you're telling the E2 you have a 1 to 5 volt signal and your minimum is 10%. So don't go below 10%. So it's going to constantly keep that at 1.44 volts or above. That's 10% of 1 to 5. So it's going to constantly keep it above that. Now, if that is not set up properly, say if you set that minimum to 0, you would have nonstop nuisance demand signal loss alarms, which I see that a lot on new startups. Like I'll see them, like the OEM will like leave it at 0 to 10
Kevin, you're totally froze.
Hey, you back?
Yeah, you're back now. So
Okay.
you start off with you see OEM when you get the rack.
Yeah. A lot of OEMs will actually have these scales wrong when they show up, depending on who programmed them, and they'll be still set up to 0 to 10 volts. So you'll have nonstop issues. So I don't know how many times I found that even a year afterwards, they're still set up wrong. So you just need to be really mindful that the output scaling. So if you're having issues with demand signal loss, that's the first place I'm going. To make sure that output scaling set up, and then the actual minimum is in there, so that it's like, not dropping it below 10%. So on like page 10, they're going to show the actual curves of how it works. So like at 1.5 volts, it'll be like roughly like 10%. You want to say 3 volts, it's at 50%. 5 volts is at 100%. And then same thing with a 3D, or I'm sorry, a 4D. So at 2.9 volts, basically, it's going to be at 50%. And then at 5 volts, it's at 100%. So a 4D can only go 50 to 100% because you're only unloading one head. So it's going to step up. So you have 50 to 100%. I do not like the digital 4Ds. You don't get as much capacity control with them as you do as a 3D. They don't seem to react as well. I mean, you got to have a pretty tight sized rack for the 4D to work properly. You want to choose a compressor. Like I tend to try to choose a compressor if I'm doing a retrofit, which I've done a ton of, probably over like 50 of these like head retrofits. I tend to choose the compressor if I'm looking at the rack, which covers the greatest range. And if I'm looking at the rack controller, the one that the rack controller is favoring the most with the most runtime, because that compressor is handling the load the best. So it'll probably handle the load the best over the range. And if I'm going to choose this, so say if we're doing like a retrofit for a digital compressor, I'm always going to choose a 3D because I have that greater range. So that's one thing to like look out for, because I mean, if I have to use a 4D, I will, but generally I try to stick with the 3Ds because they tend to work a lot better and it's a lot smoother control.
Has anyone ever tried to put two digital unloading heads on a 4D?
Emerson is not, but I'll tell you what, Bitzer will let you do all three on a 6-cylinder, and it works great.
Well, no, I'm wondering because like if you basically if you'd slow down the reaction time and slow down, like not let it jump increases, and basically let it kind of just set voltages up like that. I'm wondering if you would get a really good suction control by doing that.
I'm sure it would, because I mean the Bitzers, I did a rack, and it had two. It was a double stack rack, and it had two 60 horse. The leads were 60 horses. I did all three heads on there. So it was 6 heads total on 2 different racks. And I was running them, on one head half the time. But it took the suction group from cycling like 600 times a day on a compressor down to like 2.
What controller are you using to actually do that for the Bitzers?
So the Bitzers have like a Siemens logic controller they built in, but now Bitzer just released. I've yet to do one. I'm trying to sell one right now to somebody. They have their own integrated Bitzer module. Like it's all Bluetooth to a phone. And apparently this thing is like, on the money. Like it's like, I've seen some of the graphs and it's pretty impressive.
The only reason why I'm asking is because like I know the Siemens controller I figured that's what you were going to say. So the Siemens controller that you're referring to, like it has a memory card in it. So a lot of times if it's not programmed, where, for that amount of heads on that particular compressor, you'd have to get that memory card basically, reflashed, correct?
Yeah, so those bits or memory cards, there's like, oh man, maybe like 8 or 9 of them. So there's ones like there's different programs in there because you could actually control multiple compressors with that. There's programs in there for 3 heads. There's programs in there for controlling 2 4-cylinder compressors as digitals. So like there's all kinds of different, and then there's ones that are those are 0 to 10, but there's also cards that are 10 to 0. So that's one thing you got to really watch with those because 10 volts is full on load on some of those bitsers, and then 10 volts is full load. So like you have to look at what card you have and how the EMS is set up. So that to me that's a whole problem because there's too much chance for the parts department and the OEM to mess that up with all those different ones. But the new bitser control is 1,000 times better. I looked at a bunch of stuff with it, and I'm pretty impressed. So, but yeah, I mean, their 4D control is way better than the Copelands. I mean, because you actually have the ability to do it. I don't see why you couldn't do it with Copeland, but they don't let you.
Carlisle has their own model as well, but I've never seen it. I've never got to play with one.
We have one store with it, and I'm going to be honest to you, like I've had nothing but problems with it. And last summer we had the discharge sensor failed. Okay, it failed in June. They just got the sensor in February.
There was nothing they could have swapped it out with. There was
nothing. It was like some off the wall like sensor. I ended up having to go there and put a resistor in there because I mean it was a glycol rack and it needed that compressor to run properly. And they were like a national back order. I mean, so the way Carlisle does it, they have a couple different versions. They have a pulse width modulation where they're doing the heads, and then they have one. I did a store with compound coolers. So obviously you can't really unload a compound cooling head. So what they were doing is they were using a rapid fire Sporlan solenoid, and they were pulsing the suction line. So they were pulsing the suction line to the compressor. That's how they were doing the digital unloading.
Yeah, I don't like it. I don't like it at all.
I didn't like it either. I mean, the compressor ran really hot, and it was kind of weird. I mean, I have only seen that was one store I seen with it, and that was all the Carlisle goes at that. Most of the Carlisles I see are on VFDs.
So just to let you guys know, so the reason why there are some why some of these cards would be set up or why the analog output would be set up differently. If you think about it, the analog output is basically driving this particular system to either be loaded or unloaded. So if you lose your analog output and it's 100% at 10 volt and you don't have that analog output, then basically you're shit out of luck. You're not going to have the analog output signal to actually drive whatever you need. So the idea is nowadays with a lot of different stuff, they'll make it fully loaded or fully open at 0 volts. So in case you do lose that analog output module, you're not screwed. You can still function. I remember telling you, man, this had to be at least 7 or 8 years ago. The motor, the MPEST condenser fan motors that basically have their own VFD per each one. Now I think all of them are programmed at 0 volts. They run 100%, but they used to not be. They used to actually all be programmed where it was 100% at 10 volt. And I had lost an analog output module. This store was up in Connecticut. It was 63,000 square foot. It was one of the biggest. It was there had to be at least 13 compressors on this rack. The glycol lines were just huge, and the rack wasn't running. I was screwed. I didn't know what to do. I'm freaking out. Everything is running warm because everything is running off this glycol rack. And I'm pacing back and forth trying to figure out where I'm going to get DC voltage from. And I just, all of a sudden, I'm thinking battery. I can hook 9 volts to it. So I went down to my truck, hooked up a 9-volt battery up to it, and she ran about 90% on the fans. And I had to write in my report 3 days later that I had to change out the battery on the condenser, and my boss kind of flipped some shit. But other than that, it worked, and it worked. So we got the new analog output module into it.
Yeah, I got a real good one. A quick story, real good one of those. So, Walmart, you know how a lot of them have the standalone drives where they're actually controlling. The drive's actually controlling the condenser. Well, one of my really good guys is out there, and he went out there to help somebody, and the actual condenser control board failed and took out the transducer also. So he had no transducer and he had no condenser control board. And also somehow, I don't know how this happened, but the compressor control board also was out. So they lost basically every form of DC voltage in that rack. So what I had my guy do is there was AOMs there, which are analog output Novar cards. So I had him take the AOM. He put a CPC transducer in. I had him take the AOM, put it at 50%, which is 5 volts, which powered the CPC transducer with 5 volts. Then he reprogrammed the Danfoss drive, rescaled it for the CPC transducer instead of a Novar transducer because it was piggybacking its signal off the Novar transducer. He reprogrammed it for that and made the thing work. Now, it was like 10 degrees outside, so without the drive, they weren't going to make it, especially with the condenser control board being bad. But he was able to steal power off the AOM output by keeping it at 50% and supplying the CPC transducer with 5 volts because the Novar transducer needs like 24 volts. It was like 12 to 24 volts DC.
10 to 36. 10 to 36.
10 to 36 volts DC. So, yeah. A CPC transistor only needs 5. So we were able to power that CPC transistor. It ran like that for like 3 weeks until the condenser control board and the compressor control board came in. But, that's a little bush fix you could do. If you need DC voltage, like Brett said, that's a quick way to get it. If you got an analog output card, now you got DC voltage. But one thing.
Single generator.
Yeah. We didn't have one of those at the time. But one thing I really want to go over, I want to stress this on these IDCM controllers. They're good controllers, but you need to really follow the instructions when you're doing them. And I'm going to go over a situation that we had, and this was like a massive issue. So I was at a company for a while. They had this one particular customer, big national customer, and digital compressors and their protocols, digital compressors in each rack. So I'm going around all these stores and all these digital compressors aren't working. None of them. Like half of them from a certain date code, these protocols aren't working. And their compressor protector trip. Well, these guys, nobody could figure it out. They replaced a bunch of boards and they kept failing. And basically what happened was they were blowing up the analog output cards in the CPC controllers. So some of them would blow up right away. Some of them would last, a week. Some of them would last a month, and they would blow up. They would blow up the output. So the first one I went to, analog, I would get no DC voltage out of the output. So I swap out the board, turn it on, boom. Board blows up. Okay, I'm looking at it. Everything's according to the print. How Husband sends it out. I'm looking at it, and then I realize that the commons of the actual analog input and the transformer, 24 volt supply to to the actual IDCM they're bonded, they're the same. So if your polarity is off, it'll blow the board up. It'll blow the analog output card up, because now you're sending, 5 volts versus 24 volts. Boom, potential difference, they're going to blow up. Okay, that was the issue on this one. But the other ones where they're having all these issues is, so this particular customer had a multi-flex board running the compressors and the AO, and they had a analog input card in there. So they had a center tap transformer. So they center tapped the multi-flex board. Okay, so from ground to positive is 12 volts. From ground to negative is 12 volts. Okay, the IDCM transformer is now out of phase because ground to common is 12 volts, not 0 volts. So it's out of phase. So it was every time the voltage would spike up a little bit on the transformer, it'd blow the output out on the board.
So it would blow the Triac out?
No, it would blow the AO on the Emerson board, on the CP multi-flex board.
Oh, okay.
Because it'd be at a potential difference than the IDCM. So it was shorting out the analog output cards. So what I do, and I still do this on brand new protocols because I see it every once in a while, because they still keep Husband's consistent. They consistently make the same mistakes over and over again. I mean, but I'll take that than like the random, I'll take the consistency. I'll end up rewiring the IDCM to the board. The reason I do this is that way if somebody fucks the polarity up, it's not as big of an issue. So I'll power the IDCM off the same transformer that the board's powered off of.
You got anything else?
No, I think that's pretty good, coverage on that.
Kept it under an hour.
Yeah. Yep. Well, thanks, guys. I appreciate it. Have a nice night.
All right. Thanks, guys.